Hello everyone, my name is Sierra Grant and I'm a graduate student at Boston University. Today I'm going to be talking about an ALMA survey of protoplanetary disks in the star-forming region Lynds 1641. This is work that my co-authors and I will be submitting for publication by the time you see this video, so I hope you see the full paper for more details. First, I want to start with this cartoon of a protoplanetary disk where we have a pre-main sequence star surrounded by a disk of gas and dust. These disks are the sites of planet formation, so understanding how these disks evolve can help us understand the planet formation process. Specifically, I want to talk about disk evolution in the star-forming region Lynds 1641 or L1641. This region is located in the Orion Molecular Cloud A at a distance of about 430 parsecs. Over on the right, you can see this image of Orion. You can see Orion's belt. To the south of that is the Orion Nebula cluster, and L1641 is this region extending to the south of the ONC. If we zoom in on this region, you can see this column density map here. L1641 is around 1.5 million years old, and McGath et al. In 2012 used Spitzer observations to identify around 900 young stars with disks, or class II objects in this region. In addition to those 900 class II objects, L1641 is also home to over 200 protostars. These were recently the focus of the Orion Van Dam survey led by John Tobin. L1641 was observed with Herschel as part of the Herschel Orion Protostar Survey, or HOPS. This survey was really focused on the protostars in Orion, but among those protostellar fields, 180 class II disks were serendipitously observed and detected at 70 microns. Of those, 76 we flag for various reasons, leaving us with a sample of just over 100 disks with 70 micron detections in L1641. So here on the right, I'm showing a column density map. The Spitzer identified class IIs are shown as the small red points. The large red squares are the Herschel coverage, showing the Herschel observations in this region. The blue points represent our Herschel targets, and these will end up going on to be our ALMA targets. And in white are the Herschel flagged objects. So in 2018, my co-authors and I published these results looking at these Herschel observations for 104 disks in L1641. We found that this region has a large population of transitional disks, around 23%. We found that the spectral energy distributions of the full disks in this region are very similar to those in Taurus, so we think that these two regions are at a similar stage of evolution. And lastly, we used irradiated accretion disk models to reproduce the 70 micron emission for these disks. We found that the observations are consistent with models that have dust settling in the outer disk. So I'll show a representation of that here, where the small dust grains in the disk atmosphere have settled to the disk midplane, where they can more efficiently grow and form planetesimals and the cores of giant planets. So we think that the disks in L1641 have plentiful dust in the disk midplane, and there's no better observatory to observe those cold dust grains than ALMA. So that was our next step. Our ALMA observation goals were to observe 99 disks in L1641 at 1.33 millimeters in band 6. We hope to get dust masses and radii, get gas properties, and then to compare L1641 to other regions and to the protostars in this region. I will note that this is a biased sample. These are infrared bright disks that are observed with Herschel, and so they might not be representative of the whole sample, of the whole region. In cycle 7, our observations were taken. So here I'm showing a subset of the continuum detections at 1.33 millimeters. Of the 99 disks that we observe, we detect 86 in the continuum at the 4 sigma level. So this is a quite high detection fraction. We detect 32 of these disks in 12CO, 15 in 13CO, and 4 in C18O. Although we have limited angular resolution in this survey, we do radially resolve 20 disks in the continuum for which we can get dust radii. And one object shows large-scale structure outside of the disk, and I'll show images of that shortly. So first, dust masses. We can use this millimeter flux to get dust masses since those two things are proportional. So here I'm showing the dust mass for all of our targets, with upper limits shown as the downward-facing triangles. Transitional disks, these disks with cavities, are shown in blue, and resolved disks in the continuum are shown in red. I'll just zoom in here on the most massive disks to show that these massive disks are often resolved, and some of them are transitional disks. So now I want to compare L1641 to other regions. So here I'm showing a cumulative distribution as a function of dust mass. So you can see the L1641 protostars are in the light blue there at the top. Just below that is the L1641 class 2s in our sample. And then below that, you can see that collection of colored lines represent these other regions that have been surveyed in the millimeter. And so you can see that those are quite tightly packed. And you can see, for instance, Upper SCO in green, sort of an older region, falls to the bottom, indicating lower dust masses. I just want to note the height on the y-axis here corresponds to the detection fraction of the survey. So ours goes up to about 0.9, so that's the around 90% detection fraction that we get in this survey. So L1641 class 2s sort of stand out from the rest. And I just want to remind you that's due to our high detection fraction, and also that our sample is biased. So I want to bring this picture back where we have all those little red Spitzer identified class 2s, and we only observed 12% of those in L1641. So we're biased towards these infrared bright objects. If we instead pretend that we observed all of L1641, the other 88%, and we have a conservative limit that we don't detect any of those 88%, then that's what we would get here in this black line that I'm indicating with the arrow. So while we can't really say where L1641 as a whole lies on this distribution, we do have an interesting subset of the population that we can do interesting science with. So our sample is biased, but it's still an interesting sample to compare to. So here I'm showing the same information in a slightly different way, where this is the distribution of dust masses. The L1641 class 2s in our sample are shown in black, and that's the same on every panel. In gray are the comparison surveys that we're looking at. And these comparison regions increase with age as we go to the right. So for instance, in the top left corner, you can see that the L1641 protostars lie at higher dust masses than the class 2s. There are some outliers, but sort of by the time you get to older ages, for instance, Upper SCO in the bottom right corner, the dust masses lie at lower distributions. So these dust masses are decreasing with age. Here I'm showing the gas fluxes for the objects that we do detect in the gas. So the 12CO flux is shown in black, the 13CO is shown in blue, and the C18O is shown in green. And so while there is some scatter, we do find that with increasing 12CO flux, there is an increase in this 13CO flux and C18O flux. I will note that some of these objects over to the right are not detected in 12CO, but we do detect them in 13CO, and in one case also in C18O. One object in the sample shows large-scale structure outside of the disk. So here I'm showing the continuum on the left, 12CO, 13CO, and C18O. And so you can see this really beautiful arm that's coming off of the disk to the south. And you can even notice in the 12CO, at the location of the disk, there's little emission in 12CO, perhaps indicating self-absorption. So we think that this Large-scale structure could be indicative of a remnant envelope around this object, perhaps sort of bridging the gap between class 2 objects with no envelope and younger objects that have not yet cleared their envelope. What I hope is next is to do a complete unbiased survey of Lynds 1641. So bringing us back to this picture, there are hundreds of objects here that we can use to study disk evolution theories, and I think a complete unbiased survey of this region would tell us a lot about how disks evolve. I'm also hoping to do targeted high-resolution follow-up of the large sample of transitional disks in this region to understand how these disks are evolving internally. So here I'll offer my conclusions. L1641 has a large population, hundreds of disks across evolutionary states. Combined with the protostars, there are over 1,000 objects here to study. While we only observe a subset of the L1641 and a biased subset, these 100 disks show evidence of significant dust settling, and that's seen with the Herschel data. But these disks are also quite massive, with a mean dust mass of 12 Earth masses, and that's seen with the ALMA data. One object shows this potential remnant envelope emission, potentially bridging the gap between class 2s and the younger protostellar disks. We have big plans for what's next, and if you want to be involved, we'd love to have you. I hope you reach out to me. So thank you. If you have any questions or any feedback, please email me. I also work on accretion in intermediate mass stars using near-infrared spectroscopy, which I'm happy to talk about. I'm also on the postdoc market, so if you have any opportunities and you think that I can help contribute to your science, I'd love to talk more. Thank you.